Hello everybody, and welcome to our webinar. My name is Vladimir Podnos. I am Director of Marketing and Support of Terra Analysis, and today we will discuss simulation of the pulsed power devices and technologies in QuickField. Pulsed power applications are used in various fields of engineering, physical researches, biology and medicine. Powerful industrial lasers, nuclear fusion, medical applications, agricultural innovations. This list is long and still growing. And these devices and processes require extensive simulations to achieve optimal performance, decrease costs, and simply make them working. And we have many customers using QuickField for various aspects of pulsed power application simulations, so today we decided to show you how we understand them using QuickField for this kind of applications. This webinar will consist of two presentations. I will explain why QuickField is so efficient for pulsed power simulations, and then my colleague Alex will show live examples of pulsed power technology components simulated with QuickField. QuickField is multi-physical finite element software supporting many types of field analysis. They are grouped as electric, magnetic, and thermostructural suites. Electric group includes electrostatics, AC and DC conduction, and also transient nonlinear electric analysis. Magnetic suite combines DC magnetics, AC magnetics, and transient magnetic analysis packages. Thermostructural suite includes static and transient heat transfer, and also stress analysis. Pulsed power application may require any of these models. In some cases, static simulations may give you enough information to improve the design, especially if you need to find proper shape of your electrodes. And AC models may be convenient for fast evaluation of electromagnetic processes, even if your pulse shape is not purely sinusoidal. But for most accurate analysis, it is usually required to define the exact pulse shape, and this needs you to use built-in functions which are present in transient electric or transient magnetic models. And transient heat transfer model may be required if you need details of heat dissipation produced by pulsed electromagnetic field and to see how it develops in time. So this slide highlights transient models available with QuickField. Stages of solution of QuickField are always performed following the same workflow. First, you should define type of analysis. Then you specify geometric model. You may draw it in QuickField using our model editor functions, or you may import it from other CAD systems like AutoCAD or SolidWorks. And then the mesh should be built. We have automatic mesh, which is usually sufficient, but experts may adjust the mesh manually in very large amounts, so you may do manual meshing as well. But in majority of cases, for first simulations, our automatic mesher is efficient enough. After you build the mesh and define geometry, you need to define physical properties of materials and field sources. And if the model is fully defined, you simply press the button and in short time get the results. QuickField allows simulation of models with various types of media, including linear and nonlinear. In nonlinear media, the properties are dependent on the field level. It supports various types of the field sources. Wide range of the built-in functions allow defining any shape of pulses for the field sources. These functions include common functions like sine, linear function, and pulse-specific functions, so impulse, step function. Transient problem results show field pictures for each time layer. QuickField allows to switch the time layers and also build the graphs of local and integral values versus time. Pulsed power application often require several types of analysis for the same geometry, which cover different aspects of device operation. Electromagnetic fields may generate considerable heat, and this may require heat transfer simulations. electromagnetic forces may cause mechanical concerns and lead to coupled electromagnetic stress simulations. QuickField provides tools for this kind of applications as well. On this slide, you see how to combine several types of field analysis on the same geometrical model. If the built-in functions and features of QuickField are not enough, there is an easy way to expand them using an open object interface to QuickField core, which is called ActiveField. This allows linking of QuickField with MATLAB scripts or Microsoft Office macros, or prepare custom programs written in C++ or any other programming systems which supports open object interface. ActiveField application programming interface provides access to the functions of the graphical user interface and allows automation of routine tasks, performing additional calculations, including QuickField into the higher level simulation system or any other task which is impossible using only graphical user interface. And most important, QuickField, regardless of this rich set of options and analysis capabilities and high performance, it is an extremely easy package which requires practically no specialized training. And now my colleague Alex will demonstrate how to apply QuickField for pulsed power applications in real time on live models. Alex, please continue.
Today we will review 6 cases. First is the disk capacitor, and the voltage pulse is applied to the disk capacitor and the charging current is calculated. The second case is the lighting arrestor. The lighting voltage pulse passing through arrestor will be simulated. The third case is the multi-turn coil, and the voltage pulse is applied to the coil and the current is calculated. Then we will review the pulse transformer and 2 additional problems: the coil heating by the pulse current and the mechanical stress in the coil. The first case is the disk capacitor. Disk capacitor consists of 2 plates made of metal and the dielectric layer between the plates. The voltage pulse is applied through the terminations. Our task is to calculate the current as a function of time. Capacitor dimensions and the material properties and the pulse parameters are shown on the slide. Now I run QuickField, our simulation tool, and first I create the new problem. Here I should specify the problem name and the folder where the files will be stored. I call the problem the disk capacitor. Then I choose the problem type. The capacitor stores the energy in the form of electric field. And to simulate the transient process in electric field, I choose the transient electric problem type. The model class is axisymmetric. The model class defines how the program should treat our 2-dimensional sketch. Axisymmetric means that the geometry features rotational symmetry. The axis of rotation is a horizontal one, and in the model we should draw only the upper half of the cross section. The length units are millimeters. For transient problem, you should also specify the integration time and the integration time step. I believe the capacitor will be charged in a very short time, so I set 10 milliseconds as the final integration time. As for the time step, I have no idea about time constant of the capacitor, so I let the program to choose the proper time steps automatically. Now the problem definition is ready, and I press the finish button. You can see here the problem tree pane and the geometry model window. Let's build the geometry model. This is the dielectric layer. These are the conducting plates. And these are the termination. The geometry model is ready, and the next step is to assign labels to geometric object. I set the label to this block. This is the dielectric. And other blocks are conductors. And I set the label to the grounded terminal, ground, and to the voltage terminal. Now with the labels I can identify geometric objects, and I can assign physical properties to geometric objects. For the conductor, I specify the conductor electric conductivity. The electric conductivity of copper is 56 times 10 to the power of 6. For the dielectric, I specify the electric permittivity of the electric. It's 4. For the grounded terminal, I specify the 0 voltage. And for the voltage terminal, I specify the 1 kilovolt pulse. The geometry model is ready, the material data are ready, and the next important step is to build the finite element mesh. To build the mesh, you should press the button Build the Mesh. The mesh will be built automatically. Now I can save all simulation files and start the solving process. You see, QuickField automatically chooses the time steps and calculates the field distribution for each step. The solution is ready, and we can take a look at the field distribution. Here you can see the lines of equal electric potential in the final moment of time. In transient problems, QuickField calculates the field distribution for each time step. You can select the moment of time from the list, and you can choose the values to display on the picture. Now I will switch on the vectors of electric field strength and the color map of the electric potential. Here is the color map and the color map scale, and these are the vectors of electric field strength. And the lines are the lines of equal electric potential. You can measure the field values in every point. Just click inside and get the field values. These are the local values, and you can also calculate the integral values. Let's calculate the current in conductor. I will build the integration contour and choose the proper integral in the list, the active current for the given surface. This is the momentary value of the current for the specific moment of time. And I can also make a time plot and see the current changing in time. Let's zoom in and take a closer look to the current. Now we can see that the current rises to a very high value, and then while the capacitor is charging, the current fades to zero. I can use this time plot to estimate the time constant of the capacitor. Now I know the current value in time, and in the field picture I can get the current density distribution. I will adjust the field picture, switch off the vectors, switch off the potential lines, and switch on the color map. You can see that in this region the current density is very high. And QuickField allows easily modify the design and test different models. Let's add some metal filling here and check the current density again. I go to geometry model. This would be the metal, the conductor. I build the mesh and run the simulation again. Again, QuickField calculates field distribution for every moment of time. Now let's switch on the column map of the current density. And compare the design without metal filling and with metal filling. You see that the current density here is much lower than in this place. Next, it would be interesting to check the electric field stress value. So I will switch to the last moment of time when the capacitor is fully charged and the field strength is maximum. And I will switch on the color map of electric field strength. Inside the dielectric, the electric field strength stays at the safe level, but in the air close to the disk H, the field could be much stronger. To calculate the field in the air, I should add the air in the model. So I switch back to the model and add the block. I give the label to the block, it's air, and I specify the electric permittivity of the air 1. I build the mesh and run the simulation again. "20 seconds and the results are ready." And here you can see the field distribution in the air. Now let's take a look at the electric field stress. Again, I switch on the electric field stress value and switch on the column map. Indeed, there is the high value of electric field strength close to the disk H. And with QuickField, you can easily adjust the design. How to reduce the field? I will just modify the disk plate run the simulation. This modification should reduce the electric field stress. Again, switch on the color map. Indeed, in this part, the electric field stress is reduced. That is the way you do simulations with QuickField. It's fast and very easy. Next case is the lighting arrestor simulation. Lighting arrestor consists of ceramic tube. Inside the tube there are the tablets of semiconductor, the zinc oxide. The lighting arrestor is used to protect the insulation and the conductors from the damaging effects of the lighting. The arrestor has two terminals, the ground terminal and the high voltage terminal. The nominal voltage rate is 35 kilovolts. In normal condition, the current for the arrestor is very small. When the lightning surge arrives and the voltage level rises to the high level, the semiconductor resistance reduces and the current flows through the arrestor to the earth. The lightning pulse has 20 milliseconds long rising front and fades in 18 milliseconds. The pulse peak voltage is 200 kilovolts. Now start QuickField to simulate the lighting arrestor. The program is already prepared. The problem type is transient electric, and the model class is axisymmetric. The arrestor features the cylindrical symmetry, so in a geometry model only the upper half above the rotational axis present. In QuickField, the axis of rotation is a horizontal one. For transient problems, the timing should be specified. The integrational time step and the final time step. And here is the geometry model. In geometry model there is the air block, and for the air the electric permittivity is specified. There is the ceramic block, and electric permittivity of ceramic is specified, and electric conductivity. And there is the semiconductor block. For a semiconductor, I specify electric permittivity and the electric conductivity. And the electric conductivity depends on the applied electric field strength. It's a nonlinear material. On the ground termination, the zero voltage is specified. And on the high voltage termination, the voltage value is specified by the formula. It's the sum of the nominal voltage, 35 kilovolts, and the surge pulse. Now let's take a look at the field picture. You can see the equipotential lines at final moment of time. In transient problem, QuickField calculates the field distribution for several time steps, and you can select the moment of time from the list. And you can choose the value to display. I will switch on the electric field strength. And now let's take a look how the field picture changes in time. The nominal operation, then the pulse arrives, then it fades to zero. Another way to see how the values are changing in time is using the time plot. Just click any point and choose the time plot. I will click close to the high voltage termination and switch the value to electric potential. This is the surge pulse. The nominal voltage level is 35 kilovolts, and the lightning pulse has the value of 200 kilovolts. And you can use the contours to calculate the integral values. I will plot the contour here and calculate the active current for this cross section. This is the momentary value of the current for the specific moment of time. And I can switch on the time plot for integral values too. This is how the current changed in time. The coil is another common element of the pulse devices. This coil has 275 turns and the air core. The square voltage pulse is applied to the coil terminals. The pulse amplitude is 100 volts and the pulse duration is 1/100 of the second. Our task is to calculate the current. Now I start QuickField, our simulation tool, and first we create the problem. I will call the problem the coil. Then I should specify the problem type. The coil stores the energy in form of magnetic field, and to simulate the changing process in magnetic field, I choose the transient magnetic problem type. And the model class defines how the program should treat our two-dimensional sketch. I choose the axisymmetric as the coil features the cylindrical symmetry. And the length units will be millimeters. For transient problem, you should specify the integrational time and the integrational time step. I will set the time step to 20 milliseconds. It is 1/5 of the pulse length. And the calculation time to 0.2 seconds. Now the problem definition is ready, and I press the finish button. This is the problem tree pane, and this is the geometry model window. Let's build the geometry model. I will import the geometry model from the .exe file. .exe is the AutoCAD two-dimensional interchange format. The file is importing now. Again, I need only the upper half of the model. So I remove all objects located below the axis of rotation. And I will add the block that will be the air. Now the geometry model is ready, and I should assign labels to every object. This is the air. And this is the air. And the coil consists of conductors and the insulation between the conductors. So these are the conductors. And this is the insulation. And I set the label to the external boundary. Now I should specify the physical properties for each label. In magnetic problem, I specify the magnetic properties. The magnetic permeability of air is 1. The magnetic permeability of copper is 1, and the conductivity of copper is 56 times 10 to the power of 6. And the conductors are connected in series. For the insulation, I specify the magnetic permeability 1, and for the external boundary, I believe that the field fades to 0 far away from the coil, and on external boundary I specify 0 magnetic potential. Now I should specify the sources. I can specify the sources directly here in the label properties, but the more convenient way is to add the external electric circuit. To connect the electric circuit to the problem, I open the problem properties and type in the circuit file name. Here is the external electric circuit. The file will be created automatically. This is the electric circuit editor window. In the circuit editor, you can build the circuit using the resistance, capacitance, and the inductance element. And you can use the voltage source and the current source. In the circuit, you should include all the conductors. So this is the conductor, and this is the voltage source. Now I connect elements. For the voltage source, I should specify the pulse value. I will use the built-in functions of QuickField and specify the pulse. So it's 100 volts. Zero is the starting moment of time, and this is the ending moment of time. Now the geometry model is ready, the material data are ready, and the electric circuit is ready. And the next important step is to build the finite element mesh. After you build the mesh, you can run the simulation. To save time, I will skip the solving process. Here is already solved problem. You can see the field lines for the final moment of time. In transient problem, QuickField calculates the field distribution for each time step. You can select the moment of time from the list, and you can choose the field values to display. Here is the flux density and color map. We have the external electric circuit connected, and both the field and the circuit simulation results are available. Here is the circuit simulation results. I can see how the current changes in time. This is my voltage pulse, and this is the current changing in time. The same value of the current I can get in the field window. I should select any of the conductor. Go to the integral pane and calculate the total current. This is the momentary value of the current, and I switch on the time plot. And from the time plot, I can calculate the time constant of the coil. The next case is the pulse transformer. The transformer consists of primary and secondary windings. There are 13 turns in the primary winding and 200 turns in the secondary winding. The coils are placed inside the ferrite core. The coils carries pulsed current, and the form of the pulses is the saw. To reduce the cross saturation, there is the air gap. And our task is to calculate the magnetic field value radiated through the air gap. Here is the QuickField simulation problem. The problem type is tangent magnetic field, and the model class is axisymmetric. We have the cylindrical symmetry in the model. And we have the electric circuit connected. For transient problems, the time step value and the integration period should be specified. And here is the geometry model. In the geometry model, I have the air, and for the air, the magnetic permeability is specified. I have the ferrite core, and the permeability of the core is 400. And I have the primary and the secondary winding. For the winding, I specify the magnetic permeability of copper. The winding is made of copper. And the conductivity. The turns are connected in series, and the field source is specified in electric circuit. And this is the electric circuit. Here you can see the current sources connected to the windings. These are the currents measured in real device, and our task is to calculate the magnetic field produced by these currents. The currents are defined using the saw function. Here is the saw function definition. Now let's take a look at the simulation results. There are field and the circuit parts in this problem. In the field part, you can see the field distribution. This is the field distribution in some moment of time. You can choose the moment of time to display the field values at other moments. And you can choose what values to display. Let's switch on the color plot of the flux density. I will switch on the animation. The red zone is the area where the magnetic flux density is above 1 millitesla. And I can get the exact values in every point. And I can see how the flux density changes in time. Now this is the answer. We know the flux density value and we know the frequency and the shape of the flux density. This was the field part of the simulation, and we have the circuit part. In the circuit part, I can see the currents in the windings, and I can see the voltage pulses in the windings. Next case is the simulation of the coil heating caused by the pulsed current. And this is the multi-turned coil that is connected to the voltage source. The voltage source has the form of the periodic saw function. The pulse duration is 1 millisecond and the pulse between pulses is 9 milliseconds. The coil is cooled by the air and the convection coefficient is 10. So there are two tasks here. The first one is to calculate the losses and the second one is to calculate the temperature. Here is the first simulation problem. The problem type is transient magnetic, because the coil stores the energy in the form of magnetic field, and the model class is axisymmetric. There is the electric circuit connected, and for transient problem, the time steps and the integration time are specified. Here is the geometry model. In the geometry model we have the air with magnetic permeability of 1. And we have the coil with magnetic permeability of 1 and electroconductivity of the copper specified. And we have the insulation, magnetic permeability of 1. The sources are specified in electric circuit. So this is the circuit. The coil is connected to the voltage source. And so is the periodic saw function. The pulse length is 1 millisecond, and the pulse between pulses is 9 milliseconds. Now let's take a look at the simulation result. This is the field part, and I will switch to the circuit part. Here you can see the voltage pulses. And you can see the current. I can see that after 4 pulses, the aperiodic current fades to 0. So the pulses will have the same form and the amplitude as the fifth one. To calculate the heat power, I switch back to the field picture. Here I should select the entire winding. And calculate the Joule heat integral. This is the momentary value of the Joule heat integral, and I will switch on the time plot. So this is the Joule heat caused by the current pulses. And these pulses will be repeated again and again. Now I need to calculate the average power produced by one pulse from 40 to 50 milliseconds. I will switch on the timetable. Here I got all the data needed. I will copy the results from 40 to 50 milliseconds to Excel. Now this is the time, and this is the momentary power value. Let's build the time plot and see that I copied the data correctly. Yes, this is the pulse, and I need to calculate the average value. So I calculate the time increment. and the product momentary power by the time increment. Then I will calculate the total sum of products and divide by the power duration from 40 to 50 milliseconds. So this is the average power produced by one pulse, 315 watts. Now I can proceed with the heat transfer problem. So I create the new problem, coil heating. I will create the copy of the existing problem. So this way I will have the geometry model ready. The problem type is transient heat transfer. The model class is axisymmetric. And here I should specify the time step and the final integration time for the transient transfer. In the transient process is much slower than the electromagnetic process. So for the transient process I will specify the final time of 180 seconds, is 3 minutes, with the time step of 10 seconds. So this is the heat transfer problem. In heat transfer problem I do not need the air block. I will calculate the temperature in the coil. So instead of the air block, I will specify the convection boundary conditions. Here I select the coil surface and give it the label convection. So this is the geometry model, and now for each object I should specify its thermal properties in heat transfer problem. For the coil, I specify the thermal conductivity of the copper, and I should also specify the specific heat and the density. For the insulation, I specify the thermal conductivity of the insulation and the specific heat and the density of the insulation. And I specify the convection boundary condition. I set zero temperature here, so I will calculate the overheating, the temperature difference between the coil temperature and the temperature of the ambient. And I should specify the heat sources. In heat transfer problem, the sources are the power losses calculated in the copper. You can see that I should specify the volume power density of the losses. Volume power means that I should divide the power generated by the volume value. The power I know from my Excel file. And the volume I can calculate with QuickField. Here you can see the winding is selected, and I can calculate the geometry integral, the volume. So for the coil, I specify the total power losses divided by its volume. Now I can solve the problem. Here you can see is the temperature distribution in the coil after 3 minutes of the working in pulsed regime. After 3 minutes, the coil temperature will rise up to 25 degrees. This is not the real temperature, this is the temperature difference between the coil temperature and the ambient temperature. So if we have the ambient temperature of 20 degrees, then the coil temperature will be 45 degrees Celsius. The same coil carrying the same current, and I would like to calculate the mechanical stress in the insulation of the coil. And I would like to calculate the deformation of the coil. To calculate the deformation of the coil, I will use the mechanical problem. But I need to know the forces. To calculate the forces, I have to use the magnetic problem. So I have two problems. In the magnetic problem, I will calculate forces, and in the mechanical problem, I will calculate the mechanical stresses. Let's take a look at the results calculated in the magnetic problem. Again, I will switch on the circuit results. You can see that the peak value of the current is 41 milliseconds. And you can calculate the force acting on the current And next step, you should transfer the forces calculated in magnetic problem to the mechanical problem. You can do it manually, but the more convenient way is to solve the coupled multiphysics problem. So this is my mechanical problem. The problem type is stress analysis, and the model class is axisymmetric, and I have the link. I will import the magnetic forces calculated for every block from magnetic problem at the moment of time of 41 milliseconds. This link automatically converts all forces from magnetic to stress analysis. Now, in mechanical problem, I do not calculate the stress in the air. I will calculate the stress in the coil, and for the coil I specify the mechanical properties of the copper, and I will calculate the stress in the insulation. For the insulation I specify the mechanical properties. Now let's take a look at the simulation results. This is the deformed shape of the coil. Of course, its value is scaled. Here I can switch on the stress color map. From the stress color map I can see that the coil will be intact, the insulation will hold the mechanical stress, and here I can switch on the displacement color map. And from this picture I can guess the vibration value. This is how you can simulate the mechanical stresses in the coil.
Thank you, Alex. It was very interesting, and I hope our audience was able to follow you attentively. If somebody missed some part of presentation, you are welcome to find this file online on YouTube in a few days and on our website, and we also publish all examples. So there's plenty of information you may need to digest, but general idea should be clear. What QuickField is very well suited to this kind of simulations. It is possible to apply different types to analyze different physical situations, magnetic, electric, heat transfer, stress in one package, and perform a thorough analysis of pulsed power device. As I said, we will publish the recorded version of these presentations online on our website and on YouTube in a few days, and we hope to see you on our future webinars. We will publish our webinar schedule for next weeks in a few days, and hope to see you again. Thank you very much for your attention. This webinar is over. Thank you. Bye.